Last week, we introduced random variables, the discrete random variables, and there are a few of them that are so useful, so popular, if you allow me this, that deserve a name. The first one is Bernoulli. Bernoulli were a family of mathematicians. I'm not sure which one this refers to. And it's the easiest possible random variable because it can only take two values. And there is a reason why it is convenient to choose as values 0 or 1, where 0 is, if you think of it as a failure, and 1 as a success. When you add up Bernoulli's, if you have plenty of them, plenty of experiments where you're just interested in two possible outcomes, then when you add them, you just see the effect of the 1, and 0 gives no contribution. So you just have a nice expression for the total number of successes. This random variable has only one parameter, p, that models the probability of success, because the other, as the probabilities have to add to 1, and you just have two possible values, you just have to specify one of them. The other happens with probability 1 minus p. Is this clear? Binomial. It starts being a bit more interesting because you have not one experiment, but n of them. Each of them has two possible outcomes again. Either it's a failure or it's a success. And you record the number of successes. There are two parameters here, n and p. N is the number of experiments. P is the probability for each of them to be a success. Of course, this is related to Bernoulli. And we highlight this relation soon. In order to study the binomial distribution, we need the formula that you see at the very top. We did prove this formula, and it was a nice chance for me to introduce the interpretation of that fancy symbol there, n choose k, which is n factorial divided by k factorial times n minus k factorial. The last two are in the denominator. And this theorem is very useful for other units, not just this one. And if you keep studying math, you need to know that. So it was nice to have a proof here. Was that proof clear to everyone? Cool. Discrete uniform random variable. The way it's written here is awful because it confuses you with two parameters. For the moment, and almost without loss of generality, just think of m equal to 0, and you just have one parameter n. Choose a number between 0, 1, 2, 3, 4, 5, n. And if you believe of uniformity, it means that each of the outcomes should have equal probability. So you are forced to have 1 over n plus 1 in that case, which is exactly what this formula is telling you. We'll go back to that one. It's actually easy to study. But what I would like to insist today is the geometric random variable. And I would like to go back to the context when it's used. Binomial, let me allow to start with a small comparison. Binomial, let's go back to the setting. You have n random variables, n experiments, and you just count how many of those are successes. Okay? But sometimes when you have 0 success, you are unhappy because you want to study something that involves a particular specimen, right? So it's needed sometimes to wait until you have the first success. So you are not fixing the sample of experiment, you keep performing the experiment until you observe something of interest. Okay? It's clear? So the context, to put it in a less interesting way, is the following. This is just a metaphor, I think. I mean, flip a coin until you observe head. That's what I mean in terms of coin, but it's not interesting when I say you perform an experiment as many times needed as to when you observe the first success. Now, if you call x this, the number, so x, my handwriting is getting worse, is number, I use this for number, of trials until first success, first head, is observed. Do not be fooled by the narrative of the coin. You will see the same random variable in more interesting context. But I stick with the coin for the moment. If you believe that you use the same coin, and if you do believe that when you flip it repeatedly, the outcomes do not affect each other, you have independence. If you do believe this, if this is a good model of what you are observing, then what's the probability at x? First, what are the possible values of x? Don't need to raise your hand. All the integer, non-negative, actually positive integer numbers. So now, what do I use for positive integer numbers? You can choose. I have a French friend that uses n for including the zero, though. What do you prefer? Any preference? N or Z plus or whatever? Z plus is okay. So from now on, if I make a mistake, because I use N actually, Z plus is this. Okay? Do we agree? And there is no ending there. Very good. So possible values of X is Z plus, which is good. Let's ask the probability. Is this clear so far? So the probability that x is equal to 1, well, you want to have a success right away. So P is the probability of head. The probability that x is equal to 2, you need a failure in the first outcome and then a success in the second one. And of course, a natural pattern here is x is equal to n. You need to observe n minus 1 failures before, and a nice p at the end. And you keep going, of course. But then, the question is some probability of x equal to n and going from 1 to infinity equal to 1? Is there a positive probability that I wait till infinity? I never see head. That's the question. Yeah. You see what I mean? Is there a positive probability that I will never observe a success? That I'm so unlucky that I will never see one? You cannot rule it out because of the way we compute those probabilities. There are cases where the random variable can take the value infinity because it's called defective. I don't want to explain that. In any case, what I want to explain now, what I want to deal with, is to prove that this is a genuine probability mass function. Is non-negative? Well, if p is between 0 and 1, I don't see negative numbers there. Does it add up to 1? Is what I have to prove. It's clear? Is our task clear? Everyone? So I need a small digression here. I change page unless you have. I'll try to write a bit better actually. Let's see. This should be a bit better. Digression. Actually, this is one of the reasons I study math, because I really like, I was studying economics at the beginning, and what I really liked was to see formulas of this type that popped up very naturally in actuarial science. But anywhere, if you take any number, A, and you just take to the power k, can you sum this? By sum, I mean, can you have an easier expression? Now, if A is equal to 1, it's trivial. This is equal, I call this star, okay? So I don't write it all the time. Then, star is equal to n plus 1. Because I'm summing 1 each time you have n plus 1 elements in the sum, including 0, as you can see, then there is nothing to prove. Now, the interesting case is if A is different from 1. Okay? But if A is different from 1, look what I do. I consider, we already went through this last time, 1 minus A, this is a legitimate object, right? It's 1. I don't consider 0 divided by 0 here, because A is different from 1. This could be negative, not saying anything about it. And then the sum, instead of the sum here, it's convenient to see what is this sum. I didn't do anything because that is 1. If I multiply something by 1, I don't do anything. Are we good? But then, what I do is multiply the numerator out. So I should have a bracket, multiply out the numerator. And you get that 1 multiplies 1 and is 1. Minus A multiplies 1 and becomes minus A. Plus 1 multiplies A becomes A. Minus A squared plus A squared, because 1 multiplies A squared. This is the way I get the last one. So you just keep alternating the effect of 1 and the effect of A, right? A that multiplies A squared becomes A cubed, but with a minus in front. Yep. And you keep going. The very last term is an plus 1. And then I do not forget where I started with. What I started with, it's this now. The good news is that this object simplifies, this simplifies, that everything kills everything else, with 2 exceptions. Your very starting point and your very end point. Okay? So we get this nice formula. 1 minus A to the power n plus 1 divided by 1 minus A. This is true all the time, if A is different from 1. And if A is equal to 1, I even get an easier answer. So I cover all the cases. Are we good? Something special happens when if A is between minus 1 and 1, something special happens. Okay? What do you know about the limit as n goes to infinity of A and this? What do you know about this? Goes to, sorry? 0. Why? Because I think of 1/2. 1/2 to the power n is 1 over 2 to the power n. 2 to the power n becomes very, very large, very, very quickly. And as it is in the denominator, makes everything very small. Are we good? If A is negative, you could see alternating things, but in absolute value, it still goes to 0. So is this step clear to everybody that this goes to 0? If not, raise your hand or send me an email or whatever. Yes?
Can you just go through, I sort of missed the step where you're linking the ion to that. Like the 1 minus ion plot.
Yep. Well, look at the very top formula. I multiply and divide by 1 minus a. So I keep the denominator. This is what you are asking. Why is 1 minus a in the denominator? I keep that one, but in the numerator, I multiply out everything. So in order to keep the same, I need to not to forget the denominator. It's clear? Again, if this is not clear, the limit, let me know. Now, if I add 1 here, doesn't change anything. The limit is still 0. So for this particular case that I'm highlighting, what we get is that the sum of a to the power k going from 0 to infinity, which is equal to the limit as n goes to infinity, is exactly the definition of this sum in this particular case. The infinite sum is a limit. You don't do much about it. As the infinite integral is a limit. Now we know an expression for this sum. So this becomes the limit as n goes to infinity of 1 minus a to the power n plus 1 divided by 1 minus a. Are we good? Now, the limit of each of these individual objects here exists, and the limit is linear if each object involved has a limit. So what I'm saying, in a very confusing way, is that I can just plug 0 there, which is the limit of the only thing depending on n, and this is the total sum. Okay? Magic. I like it, at least. Any question? Can you read what I write? Is it clear? Let's apply this. But first, tell me if you have any doubts about this page here. And notice the coincidence. Have you been here before? There was some class MTH222. This is actually the distribution we are going to talk a lot about. We are going to derive. When I'm going to prove that the integral of this is equal to 1, this is the Gaussian distribution, you'll be a bit puzzled about the methods, unless you look in advance polar coordinates in 2 dimensions. Okay, just give it a look. I don't know who wrote that, but of course, any unit will use this. This is very, very important. But let's go back to what we are doing. Is this clear? So let's use it. And magic. This is exactly the way I want to use it? No, I don't care about this. It starts being a bit, it looks complicated here. But look, this is actually exactly what I wrote. So let me analyze this. What is, so what I proved was the sum k going from 0 to infinity of a to the power k. We good? Now, what happens if I have this sum k going from m to infinity of a to the power k? What is this sum? How can I get it? Well, there is an easy way, which allows us actually to introduce an extra concept. Look, you can write, so we need to, without computation, just using the result we already know. We can write this as a k minus m plus m. adding and subtracting in many of these advanced units is the answer to many complicated questions, which is, I find a bit sarcastic, ironic at least, sorry, not sarcastic. So this of adding and subtracting allows us to, in many situations, to find a good solution to the problem. This can be written as sum, k going from m to infinity, of a k minus m, a to the power m. Now, the infinite series, I'm saying something that I did not prove, it's linear. M does not depend on the integer. M is a fixed number, a fixed parameter there. So this becomes a to k minus m. It's true because the infinite sum is a limit, and I know that for a limit, so I know that if there was a finite sum, I can pull constant outside. I know that if there is a limit, I can pull the constant outside the limit. So from time to time, I have the tendency of recalling real analysis concepts. Do not worry if you didn't take real analysis. I'll make it clear what I can ask you and what not. This particular step, I don't ask. It's on a different field. Now, what is really important is this, and you should, what can I do here for that sum? To recover something that I know. Look at that sum, and let's write it extensively. So first, I use the fact that I can write this directly. What is that sum? The very first term, what is it? The second term. Yes. The third. Yes. So it's something that we know. We can write this as a change of variable. You see it a lot with integrals. We can do it with sums as well. So it's sum from j. Doesn't matter which letter you use in the sum as long as you are consistent. Right? Is this. How can we achieve this without the intermediate step? First, is this clear? I'm lazy. I didn't want to write this. So in the future, I'm not going to write this. I simply can say set j equal to k minus m. What is the very first value of j? Is 0. The second value is 1, and so forth. Rewrite the whole thing as this. Are we good? Now, it's very useful because I know what is that sum. It's a to the power m divided times 1 minus a. Because we know that this, in the bracket, is 1 over 1 minus a. We proved it. For a between 0 and 1. Or more extensively, this is true for any a between minus 1 and 1. We proved it. Any question about this? It's useful. Okay, let's apply this stuff. It's been too long. So the probability, the sum n going from 1 to infinity of the probability that x is equal to n is equal to the sum n going from 1 to infinity of 1 minus p n minus 1 times p, which is the sum p, sum n going from 1 to infinity of 1 minus p to the power n minus 1. Change of variable, j is equal to n minus 1. This becomes the sum p times the sum j going from 0 to infinity of 1 minus p to the power j. I just applied the same change of variable. I call this a. A is equal to 1 minus p. So if you call this a is between 0 and 1 in this case, because p is a probability. So p must be between 0 and 1. 1 minus p has the same property. So this is equal to P divided 1 minus A. But this is equal to P if I plug the value of A, 1 minus P, which is equal to 1. And I'm happy. We good? Binomial, you will see in the exam. Poisson, 2. 2 different questions. Okay? Now, in the exam, it will be, I never asked, I think, in the past to prove that this is probability mass function, so to go through these steps. There will be at least one question about the binomial, but it's quite, I wouldn't put too much weight on. Could be, but I consider this an easy question, even though it's complicated in terms of steps. Now, are you familiar with Poisson distribution? Have you ever seen it before? Okay. For those of you who saw it, how is used? What is the model? So let me summarize. Bernoulli, we know, you flip one coin. Uniform, discrete uniform is, you know nothing about the experiments, probably, or everything is equidistributed, discrete setting. Binomial, n experiments, and you count the number of successes. Geometric, you wait until the first success. Poisson, random variable. Yes?
Isn't it like the number of occurrences you see in the time frame?
Yep. It's the number of successes in a time frame. It's more or less what is going to happen. You're talking about Poisson processes, and it's an advanced topic. So there is one unit, a third-year unit, stochastic processes for engineer, where this plays a major role for half of the semester, and it's the hardest model there, actually. And now, I'll give you a different flavor of it. Poisson is a binomial when the probability of success is very small, but you have you do have a lot of trials. So this doesn't happen frequently, but I think it's the right moment to show you what a Poisson random variable is, where it comes from. Yeah. Do I have the time? Just a moment. Yeah, I do have the time, I don't care. Let's just do it. So, binomial with n, where consider n large, and for a moment I'll tell you what does it mean, and p, where p is small. Let's be more precise. I'm going to send n to infinity. That's what I say for, what I mean for large. And p is small, p is equal to lambda divided by n for some lambda larger than 0. Okay? So binomial, what I have in front of me is binomial n lambda divided by n. And I'm sending n to infinity. Are we good? It's clear? The setting?
What's the set lambda greater than?
Lambda greater than 0 is because I want to have a probability. Any lambda will do because if I consider n large enough, it's something between 0 and 1. So I don't consider anything negative. Lambda, for those of you is going to be the parameter of the Poisson, but it's also called rate. Now, let's find x is this, find the probability that x is equal to k, where k is a fixed. So what are the possible values? K is a fixed value in natural numbers. I include 0. Because I can have no success. Now, what is this? This is equal to n choose k. So I'm going to consider the limit, okay? I need to keep an eye on that. So this is the limit as n goes to infinity of n choose k, p to the power k, so lambda divided by n to the power k, and 1 minus lambda divided by n to the power n minus k. Are we good? We are going to study this limit and give a definitive answer. Now, let me rewrite the coefficient here as n factorial divided by k factorial, n minus k factorial, okay? Just the coefficient, and soon I'll write the rest. This coefficient here, I can rewrite it slightly differently. This can be written as n times n minus 1 times n minus 2, because it's a factorial, right? So I'll reach n minus k plus 1, and then I become suddenly lazy, and I write this as n minus k factorial. We good? I'm just looking at the coefficient. Then I'm happy because I can simplify this with this. And of course, I should write the rest, so I need to create a bit of space for lack of. Well, what I can do is to delete this, and now I have lambda to the lambda. Yeah, I can do this. Lambda to the power k, and you know what? I put n to the power k here. I move this k factorial here. Then 1 minus lambda divided by n to the power n, and 1 minus lambda divided by n to the power minus k. And of course, I'm considering a limit as n goes to infinity. I just reshuffled a few things, but I didn't cheat anywhere. This is a ratio. First, before I keep going, is this clear? Did I go too fast here? Yes? Is there below lambda k? I just reshuffled because I have a reason for that. So, n, you see, before there was n to the power k below lambda. I just moved it on the left, and k factorial, I just moved it down. Anything else? Okay. You don't have questions. I do have questions. What is the first limit there? The limit of a product is a product of the limit if you do things right. It's a finite product. Each of those things have a limit. So. Now, I analyze each of these pieces separately. What's the limit of the first object there? It's 1. How can I do it without multiplying out all those things? The reason is the following. If you have this polynomial here, so we have to cook this limit. Let me give you the ingredients. Limit as n goes to infinity of n squared plus 1 divided by n squared plus 2n plus 5 is equal to 1, because what you do, you look at the leading term here is 1 divided by the leading term here, which is also 1. Are you familiar with this? So you just look at the leading terms. You do not care about the rest, because those leading terms grow faster. I can write this. So the answer is 1. Why? Because I can write this as n squared, 1 plus 1 over n squared, divided by n squared, 1 plus 2 over n, plus 5 over n squared. This goes to 0. This goes to 0. This goes to 0. These two simplify. 1 divided by 1. Okay? So if you have two polynomials in n, and you have a ratio, the limit of this is achieved just by looking at the leading term, the coefficients of the leading term, if they have the same degree. What is the coefficient here? The denominator is very easy, is n, is 1. And the leading term is degree k. The numerator, the leading term is also degree k, so they have the same degree. And the coefficient is 1 because it can be achieved only multiplying out all the n, and all the coefficients are 1. Are we good? Good. So this is 1, and this was the hardest part. I hope. Is any question? I want to have everything on this page, so I delete this. What is the limit as n goes to infinity of 1 minus lambda over n to the power n? E to the power e minus lambda. Again, this is calculus. You might find it confusing. It's prerequisite, and it's there. If you didn't see this for a while, it's not a problem. You are not asked. Well, you are asked, but you'll be given time to assimilate this. So you have to know for this unit, and not just for this unit, for the rest. Take the log if it bothers you. Once you take the log, you can make it as the ratio of two objects that go to 0. Both of them go to 0. You can use the L'Hopital. Are you familiar with the L'Hopital rule? Very good. This object here, the last one, goes to, if n goes to infinity, well, as you can see, lambda divided by n goes to 0. So each of those goes to 1. It's a finite product because k is fixed, so that thing goes to 1. If I put the pieces together, what I get is that this limit is lambda k divided by k factorial e to the minus lambda. And this is true for any k larger or equal than 0. So natural numbers, including 0. This is the genesis of a Poisson. It counts the number of successes when you have a lot of trials and the probability of observing one is really low. Lambda over n is small, the number of trials is large, but they compensate each other. N times lambda over n is lambda. So somehow there is a compensation in the number of trials. You're looking for something very difficult to find, but you have a lot of time to dedicate. This is about modeling, so I'll give more, if I have to produce a video, I want to produce a video about how to apply Poisson in real life terms. The question that you are going to ask me is this accessible, these steps that I just showed you? No, by far. What is accessible, though, is to show that this PMF, probability mass function, is actually a PMF. So what do we have to prove? Exactly. Add up to 1, because nothing is negative here. I don't need to worry about things being negative. I have e to the power is positive. Lambda is a positive parameter, so lambda to the power x, no problem. X factorial, it's positive. Are we good? So what I need to prove? I don't want to use x, so I use k. Sum k going from 0 to infinity, the possible values of e to the minus lambda, lambda to the power k divided by k factorial. I need to prove that this is equal to 1. My task is this. It's an infinite sum with a bit of imagination, not really. It's easy to prove that this is true. I can pull out whatever does not depend on k. What is this? Taylor expansion of e to the lambda, e to the minus lambda times the Taylor expansion, e to the lambda, and this is e to the minus lambda plus lambda, e to the power 0, 1. So yes, this is true. Just prove it. It is a legitimate probability mass function. Are we good? So I have office hour today. I will ask you to, I might buy some cookies to motivate you to come. Send me an email if you plan to come, so I know how many cookies I can buy. And send it by 2 o'clock. And also, if you send it by 1:30, also which type of cookie you want to have. 2 o'clock is a kind of late for that, okay? So let me know. It's from 4 to 5. Good? Good. Any question before I keep doing this? Are we good? So next time we're going to talk about expected value, variances, how to find them. It's going to be heavy. A lot of computation. But the good news is that we're going to use the machinery that we developed. So I will ask you to analyze, okay, this limit we saw today, let's learn the power series that we just saw. That is also the Taylor expansion of e to the power lambda. See, check what is the Taylor expansion. The geometric series, we're going to use it a lot. So catch up with the tools that we saw today. They're going to be used a lot in the rest of the unit. The good news is that it's always the same, so it might be also boring for you. So my role is to find a way to challenge you a bit. And this starts with section 4. It's useless, this thing. It's fine. So section 4. But today we do not reach section 4. For those of you in MTH 2225, I can show you how these 3 simple things here were used to solve open problems that were open for 30, 40 years. Nobody could solve. Just one line using just the definition of expected value and a small trick. So we're going to see that on Wednesday. So for those of you in MTH 2225, just read what is this. An average, what is the expected value? You know what? I follow a bit my intuition and I just start with this. I don't forget that there is a section 3. So just wait a moment. Oh, by the way, we have another MTH 2222 before Wednesday, right? Tomorrow there is class, or I know Wednesday morning. So I don't follow the intuition. I don't wait. Let's do this. So sometimes we have random variables that look quite bad, 3, 5, but we do not care. That's -2, -1. We do not care about the actual value, but we care about the intensity of the signal, or forgive me, but we do not care about the actual value, but the absolute value. Okay. We do care about something that has to do with the data, but not the complete information. So you want to transform the data, and let me do it in good. So suppose that this is 1/5, this is 1/5, and I have 6 of them, so let's 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. And this is my x. I have a very simple question. Copy. Paste. And this is my x. Or if you want. These are the possible values that I wrote clumsily in the first line, and those are the probabilities. So it's a discrete uniform of a certain kind. Now, I do not care about x. I do care about x squared, or absolute value of x, or something else, a transformation. I'll transform the data a lot, because I can simplify the data. Or I want to transform the data because what I see at the beginning, I don't know it, but there is a way to transform the data to make it more familiar. For example, this guy here, I like it. A lot of people spend a lot of time to transform the data to have something similar to this, because then they can deal with it. They know what to do afterwards. So transforming the data is good. But you lose information. That's the first thing. And it's good as well. You have less information to carry. But how to transform it properly? Because I know the possible values. What's the possible values of x squared now? What are the possible values? 0 is there. 1 is there. Yep. Okay. What do you observe? Did we lose data? Did we lose information? Yes, because now I just have 5 items. But what are the probabilities? In order to compute the probabilities, because x squared inherits the probabilities from the original setting. How? What I have to do? It's very easy. So what's the probability that x squared is equal to 0? 1/6, because in order to be equal to 0, x must be equal to 0. But what is interesting is, what's the probability? Is the only interesting part that x squared is equal to 1. Yep?
Probability of x equal to -1 plus probability of x.
Exactly. The probability that x is equal to -1 plus either is -1 or is 1. Because when I square either 1, I get 1. You see, if I square -1, I get 1. And so this is going to be 2/6, or 1/3. So what I wrote now that I'm not going to finish is what is written here that you might find a bit complicated to decipher. You just say, y is the transformation of x. You want to know the PMF of y, you just have to go back to x. How you do it? If there is not one way to go back, but multiple ways, you have to sum up the probabilities, as we did with -1 and 1. I will talk more about section 3. It's the starting point of the next lecture. But keep in mind that starting from the expected value, things will get a bit hard. So be ready with the tools that we discussed before.